Today we'll finish off our discussion about conservation of linear momentum and rotational momentum. It includes kind of a discussion of maybe the trivial. The trivial here is, the garden watering machine, garden water, which of course is just an axial supply into something that squirts it out at either end and turns around. And of course, you're converting by squirting fluid out linear momentum into rotational, into torque, basically. You can imagine a variety of these kinds of demonstrations. This is, I think the sound is turned off on all of these, but this is just someone, I think, putting dry ice or liquid nitrogen into a container. I'm sure he is wearing safety goggles. I wouldn't be doing this with my hand there myself, but that's up to him. And then the idea is that this is frozen gas, which is turned into liquid. Maybe probably is liquid nitrogen, I'm not sure. Don't know whether liquid nitrogen would actually shatter that container. And then it's not very clear, but he's putting a top on it, and the top has two little hoses that come out of it. The hoses are arranged so that they're opposed, and so that when you put this container into something warm, like this beaker of water which he's about to put it into, then the gas heats up, it expands. As it expands, it gets forced out of the nozzles, and it rotates. So a kind of trivial example of a machine in that particular case. Of course, in power stations, we talked about Pelton wheels, which are these wheels that we squirted water onto these little buckets, and they turned the thing around. There are more advanced turbines to use than that. Those are certainly Industrial Revolution type machines, but more sophisticated turbines are things like Francis turbines, which are attached to a generator. It's in Hauser, German. And the basic idea is that you have some blades that you flow fluid into, and as it flows into these blades, it gets spun out into the side, so it goes through the front of this. It turns with the blades. The only place where it can actually exit are through these blue paddles at the side. And so as it does that, because the blades in the turbine are angled, just like in a jet engine, it actually takes the fluid out and kicks it out. So you could either push it in through the pipe, which is here, which is a Zusfluss, is that outlet or inlet? I guess it could be either way. I think it's the outlet in this particular case. So it goes in through the front through this pipe, it goes through the blades, and then it spins out through the other side. So again, this is just an example of turning linear momentum through water, changing its direction, and then being able to harvest the power that comes from this, the energy, the rate of doing. And we've seen the Pelton wheel before, so let's not look at this, but this is kind of a neat little machine as well. Kind of quite basic, along the same lines as the Pelton wheel for home domestic off-grid power use that we saw a couple of days ago. And this is a way to pump water. Quite clever, I think. So obviously these metal blades are being turned by the current of the water. It's 4 concentric rings of tube, which are all one tube. It's all one spiral, and as it dips down, the water gets picked up, and you can see that the water would get pushed down from here. Let's move. So it's basically an Archimedes screw being powered by the river. So it's being turned, so it doesn't need any power except for the river to turn it. And as it fills up with water, that water surface tries to keep constant as the thing goes round. And of course, as it keeps constant as the thing goes round, it would slowly push that fluid through the central spiral and into the field next door, which is what it's doing. So it's filling up a pond, which is along this pipe that goes off to the right-hand side there. So kind of a clever arrangement. But in each case, you're using the linear momentum of the stream to give you some rotational power. And so that's what we'll talk about today, momentarily. But we have to clean up some things from last time before we do that. So that's where we're going with this. And actually there's a commonality between the two things that we'll talk about today. We'll finish talking about conservation of linear momentum, and we'll just recap those things first. And then there's actually a commonality between what we'll talk about for linear momentum and rotational momentum, in that we're often interested in dealing with frames of reference which are changing. And so let's deal with that first for the linear momentum case, which we didn't cover last time. And then we'll also apply that to these rotational modes as well. So that's our plan for today. So let's skip back two slides. And so we've talked before about the idea that it matters what the frame of reference is. Our expressions for conservation of linear momentum are all relative to this static coordinate system. And we've discussed this. This is what a static viewer sees as a velocity, as a function of a boat moving at 1 meter a second and squirting water at 2 meters a second. And so we know as a function of this will be 3 meters a second. So this is static observer sees the water moving at this speed. If the boat's moving at 1 meter a second and the jet is coming out of the boat at 2 meters a second. It's vectoral, and so we're looking just at the x component here, I suppose, if this is x. And so how do we transform that to Reynolds transport theorem? So you remember what Reynolds transport theorem looks like. We've written it in a simpler terms. We've always had this term set equal to 0. There's no rate of change of accumulated momentum with time, and it's just mass rate of flow out of the system. Oops, which is this whole thing here. This is m dot, what we've called m dot, and this is velocity. So it's the product of these two. This is relative to the static frame, and so what we could do is be able to substitute in for this velocity component, which is this. And if we do that, we end up with this expression down here. I think we still, in our cases, we're going to assume that we're not looking at rates of change of these things, so we don't worry about this. But now we have this velocity term, which we had before, which is now taken up by two components. The velocity of the control surface, which if it's not deforming like a balloon is, then the velocity of the control surface is also the velocity of the control volume, because the surface is staying in its exact same configuration as it migrates. Small point, but worth making nonetheless. This term here is the mass flow rate into or out of the system, as we've turned it. So this has to be a relative term, relative to this control volume. And then we need to worry about exactly what these components are. And so if we wanted to, since we're only dealing with the steady state behavior, then we could write this expression as the relative velocity of fluids coming out of the system plus the velocity of the control surface times the mass flow rate equals sum of forces. So that's our basic expression that comes out of this. And this, I guess, is also a summation of all of these components as well. So our revised expression, and it's really just the same as before, right? It's just that this term before happened to be v. And so we've just made that substitution. What we could also do is you realize that the one term here, so we could split this up so that it was written slightly differently. And if it's written slightly differently just by taking these two terms on the left side, either the relative velocity of the flow multiplied by the mass flow rate, plus, so I'm just writing it slightly differently, the velocity of the control surface multiplied by the mass flow rate equals sum of forces. These are all vectors in this particular case. Usually, this term disappears. And the reason this term would disappear is that if it's steady state, then by definition, the mass flow rate into here has to equal the mass flow rate out of here, because we're not accumulating anything. And so if the mass flow rate here equals the mass flow rate here, and the control surface is going at the same velocity on each side, so this is only a single number, because the whole thing is just translating at some velocity of the control surface, then because the amount in equals the amount going out, then the sum of these two has to equal 0, right? So in other words, basically if it's steady state, then the sum of m dot equals 0. And if the sum of m dot equals 0, we can get rid of this term. And so certainly in the book, it's stated that basically this equation is equal to only these two components. But that's not actually sufficient if we want to do some of the problems that we'd like to deal with. And so the bottom line is that we can deal with this expression. I won't do this example, but I do a slightly different example. And that the ultimate expression that we're going to deal with is just what I just wrote before. And so it's sum of relative velocity of the fluid coming out, the velocity of the control surface, multiplied by the mass flow rate is equal to sum of forces. This is a scalar, these are vectors, etc. So a very simple example to be able to illustrate this point and to be able to illustrate the importance of having this. So in other words, I guess as a rule of thumb, since we've used rule of thumbs, if it's steady state, then mass in equals mass out. Then you can assume that you can just do W times m dot equals sum of forces. In other words, even if it's moving and it's steady state, you can get rid of this velocity of the control surface term. If it's not steady state exactly, then we need to actually accommodate these two terms. And so a simple exposition of this is our friend, which I was going to look at again. We've seen it a couple of times. And that is our the decapitated gas bottle. The Mythbusters movie. Let's just quickly show. We'll come back to this thing here in a second. It'll be the next thing up. So we've seen this a couple of times, but let's look at it again. It's kind of fun. And that is that you take a gas bottle. You should always move it with the top on it here, as you see here. And if you don't do it with the top on it, then it has the potential, if it drops, to be able to fly through the air. Incredible power vested in these. And so here they're doing this experiment. They've got a guillotine of some kind to take the top off the gas bottle. And so the one thing about this gas bottle you'll realize, of course, is that you take its contained pressurized fluid. If you take the head off it, then you have flow coming out only of one port. There's not flow going in that's replacing the flow that's coming out. So it's not, by definition, it's not really a steady state problem. It can't be a steady state problem in some respects. And so to deal with this, we need to be able to use this full expression. So let's look at this. It goes through a couple of walls, as we saw. It's quite impressive what it does. It's on this launching cradle, and it just zips through. And we saw before it goes through a couple of walls. Let's not worry about that anymore. We'll let it run in the background. We don't need to worry about it. So how do we deal with that problem? So what we have is we have our gas bottle. We have our coordinate system. We take the top off it, and let's say we get some velocity out of here. I don't know, 1 meter a second. It's not very much, is it? And let's say it comes out at a mass flow rate of 1 kilogram a second, which would be m dot. And this would be V is equal to this. Okay. So we want to be able to, we could do two things, and we can apply a force in this direction. I draw it in this direction because this is the positive x direction. So this is a positive force. So we can do two things. We can write out our expression, which we said we want to use the whole thing. And it's going to be equal to the sum of the relative velocity plus the velocity of the control surface multiplied by the mass flow rate is equal to the sum of the forces in the x direction. So these aren't vectors because these are just magnitudes, I guess, in the x direction. So we can do two things. We could hold it in place by applying a force so it doesn't move, so the control surface moves at zero velocity. And if we do that, we could just write this as VCS equals 0. And then we could solve for the magnitude of the force. Or alternatively, we could make the force equal 0. And we can solve for the volume of the velocity of the control surface. We can do each of those two things. And so if we do each of those two things, then in the first one we'll do the velocity of the control surface. We've said it's going to be 0. We have a mass flow rate of 1 kilogram per second. And we can calculate the force as a result of this. And what else do we know? Well, we know that the velocity coming out of this is 1 meter a second. It's in the negative x direction, so it's minus 1 meter a second. So the result of this, I'll write it over here because it's actually space. So the product of these two is 1 kilogram meter per second. Yeah. Sorry? Second squared. Thank you. Excellent. Needs to be, of course, doesn't it, right? And so what is this? This is the definition of a Newton is the force required to give a mass of 1 kilogram and acceleration of 1 meter per second squared. So this is equal to 1 Newton. Not very much, but that's because I think our 1 meter per second is probably a little conservative. It is negative still, yes. And so in other words, to be able to hold it in place, we've got to push in this direction an amount equal to 1 Newton. Okay. So we're holding it in place. Makes sense. Just going to try and zoom off to the right-hand side, so you have to push to the left. So it gives a magnitude. If we do the opposite, if we put the force equal to 0, but we allow this to be non-zero, then what do we end up with? We know this is 0. We have the same expression as before. The relative velocity of this is minus 1 meter per second. We solve for the magnitude of the velocity of the control surface, which we don't know. This is 1 kilogram per second. The only way that this can equal 0, which it needs to be to get the right-hand side the way it should be, is for VCS to be equal to plus 1. And so in other words, the velocity of this control surface in this particular case is 1 meter a second. So in other words, VCS equals 1 meter per second plus. And so we can use it in each of those two modes. And so the interesting thing about that is you have these two kind of n-member modalities. And if you, for instance, want to write this, want to look at what these are. If we plot, for instance, a graph of force versus velocity, this is velocity of the control surface versus the force that we have to apply. It doesn't matter that it's plus or minus 1, but when the velocity of the control surface is 0, the force is equal to 1 Newton. So this is 1 Newton. And this is 1 meter per second. So when we have 0 velocity, we have this force of 1 Newton. When we have zero force, we have the velocity, the steady velocity of the control surface. It actually has to move at the same velocity in the steady state as the fluid that's coming out of it. It accelerates. We're ignoring the acceleration term. And so we have these two end member points. And so you could imagine that either you can hold it in place exactly and not allow it to move, in which case it generates a maximum force. You can allow it to move at the maximum speed and it generates no force. And maybe in between those, if you apply, say, half a Newton to hold it in place, then maybe it only goes at half a meter per second. I don't know that, but we could do the calculation. But let's assume there's a straight line between those. So the interesting thing about that, I think, with reference to all these energy-making machines, is that by definition, power is equal to work per time. Work is equal to force times displacement and time. And of course, displacement over time is a velocity. So in other words, power is equal to the product of force times velocity. In our case, these two forces. And so if you plot power, rate of doing work, then when you're holding it static, the product of these two, because the velocity at this point is zero, the power made by your machine is zero. Likewise, at this point, it's equal to zero. But at this intermediate point, it's going to be equal to, if it is indeed half times a half, which is a quarter, and it's going to be in units of force times velocity, which are watts, Newton meters per second. And so the power that you'd have in this system would look something like this, I'd guess. The maximum is at this middle point, and it would be of the order of a quarter of a watt in this particular case, which is a Newton meter per second. Force times velocity. So it's kind of curious, right? So if you're holding it in place, you're not doing any work because it's not moving. You need to have a velocity to be able to do work. If you're allowing it to move but there's no net resistance that you're applying against it, then it's not doing any work either because you don't have a force that's applied. And so the maximum amount of work, it only provides work when each of these are both non-zero, and you'd imagine that there can be some kind of maximum value. I think in maybe last year's stuff, we did a little example of the idea of wave generation. You have a buoy or a buoy that sits on the ocean and bobs up and down with the velocity of the water, or the amplitude of the waves. And so if you think about that also, if this is going up, if a little buoy is anchored to the seabed, if you stop it from going up, then there's certainly a buoyant force which is applied, which you can calculate, right? We know that the buoyant force is equal to volume times the unit weight of the displaced fluid. And so if it's partially submerged, then you know that there's a buoyant force here. But if it's not physically allowed to move, you won't generate any power. Likewise, if you allow it to bob with the ocean current, but you don't have it tethered in any way, it won't generate any power because it's moving, but there's no force applied. So the same thing. You have to be able to allow it to jump up and down at some intermediate portion where it has both a vertical velocity and also a resistance to the force which is being applied in it. And so I think that's an interesting component in this behavior that we've dealt with. Okay? So that's the end of the stuff that we'll talk about in terms of linear momentum. The other things that we would like to deal with are to deal with the ideas of, instead of linear momentum, which is really what this expression is to come back and talk about rotational momentum. And we can define this in a variety of ways. We could go through a long derivation, but maybe it's best just doing a very, very simple analogy to be able to explain this. So trust me on this. We won't go through a lengthy derivation of this. So where are we? Whoops, not Z. We are at the end of week 7. So rotational momentum. So we'd like to be able to deal with these simple rotational machines like we saw the dog running around the garden sprinkler in the preamble for today's class. So we know that for linear momentum, the expression that we've dealt with so far is, let's write it in its simplest form, a velocity times a mass flow rate equals sum of forces. This is the expression we've just dealt with. We also know that if we want to, we can define this velocity as the component to the velocity of water coming out of the hose on the ship plus the velocity of the ship itself. This is absolute velocity relative to a static observer. So those are the two important expressions that we have, that we've dealt with so far. And that actually sums up all of our discussion of linear momentum. What happens if we want to look at rotational momentum? Well, it's moderately simple. What we could do is we could take the same expression. I'm leaving a gap here. Let's not do it as let's do it simply as just a scalar quantity, and let's allow this equal to, again, I'm leaving a gap here before the force, so there's a gap here and a gap here. And so what we could do is, in representing our simple machine, that this is our control volume. In the same way that we've belabored the point that we have x, y, z right-handed control coordinate system, the appropriate right-handed coordinate system for rotation is the right-handed coordinate system, where this is the axis of rotation and the direction of your fingers is the positive direction of rotation. So if you look at this way. And so this is the right-hand rule as well. So if z is coming out to hit me in the head, or coming out to hit you in the head, then the positive rotational direction would be this. And we'll call it v theta. And there's a lever arm, which this is applied onto. So this velocity is positive because if I look at my thumb here, it's going counterclockwise. This, in this particular case, would be a right angle because it's tangential to this. And so now, instead of dealing with forces related to this, and there would be a force that would be also in this direction, what we'd like to do is, instead of working in terms of forces, we'd like to work in terms of torques. So force times a lever arm is a torque, and also a velocity times its lever arm is also rotational velocity. So what we could do is, very simply, we could write this, we could multiply this equation just by r on both sides. And if we do that, then we end up with r v m dot, and this is just what are referred to as a torque. T-O-R-Q-U-E, which is just equal to a force times a lever arm. Force times a lever arm. And so we've done it the simple way. This would be, let's keep this as the tangential velocity. This is a mass flow rate out of the control volume. And that's the expression that we'll end up using. So this is an important new expression for us. And it's relatively straightforward to use. So, and we'll try and exercise using it. All right? So the reason that we write things like this is that the torque really is a cross product between a force and a lever arm. And actually this lever arm, instead of just being a length, could actually be a vector. And so the proper way to write this is, as we'll see in a second, is in terms of a cross product. We used a dot product to be able to define the mass flow rates. You know, it's the amount of fluid that goes across a surface, not a vector. And so the sign convention follows directly from that consideration of the dot product. If the flow is in the same direction across the surface as a normal to the boundary vector, then it's positive. If the flow is in the opposite direction into this way and the outside vector is this, then it's negative, which is the reason for our sign convention. And so if we go back to maybe just quickly look at this, moment of momentum that we deal with is really this term here, which is a torque. And it's for the case that this force that's being applied acts at a location which is defined here and about an axis which is coming out of the page at me here. And to get that, if we know that, we just get it by the cross product. So you thought you might never have any use for cross products, but of course we do. In the simplest way, of course, this cross product is just going to be equal to the force that's applied multiplied by the lever arm which it goes through. The lever arm here is just going to be this magnitude here, r sine theta. So in other words, if this is a right angle here, then the magnitude of the lever arm is equal to this force multiplied through by the lever arm, r sine theta. And so in this simple case, r sine theta is this, and the scalar magnitude of the force is this. And that's physically what the dot product is. If we wanted to be more sophisticated, which we won't deal with in this class, but it's useful just to be able to be aware of it, we can also get these things by looking at what the did I say dot product? I meant cross product. So if you imagine a condition where you have a coordinate system, which is our right-handed coordinate system, x, y, and z. This has vectors I, j, and k, which are these green ones. And we look at a flow velocity v, which is flowing in this direction, and it flows through a point which is at a location r away from the center of rotation. So we're going to look at this coordinate system. We're going to look at rotation around this static z point. So what is the torque that is applied by this velocity vector acting through a length here relative to this coordinate? So in other words, the rotation is around this vertical line, right? So vertical, the coordinate system is defined. Well, to get the moment of momentum, it's just the cross product of the radius multiplied by the velocity. If you write it out in this term, I'll let you maybe go through this yourself, but we have these are the coordinates of the rotational vectors. The only rotational vector we're dealing with here, we're looking at turning around this k. The location where the fluid flow acts through is this vector here. Location Ri, Rj, and Rk. So actually it's in the y direction. So this term would equal +1. In other words, this. And the velocity is in the minus x direction. So the velocity will be -1. And this here will be -1. And all these other terms would be 0. And so that's the setup for the problem. So if you know the coordinate system that you're looking for its moment of momentum about, this axis, or this axis, you know where the flow velocity is, which is, it occurs here, and you know where the direction of the velocity vector, which would be in meters per second, and this would be in meters. Then you can just do the cross product. Cross product is I multiplied by this times this minus this times this to get this term. J times this minus this times this. You've seen it before to get this term. And then K multiplied by this times this minus this times this. And so in this particular case, the only term that comes out of it is the terms on this final component, which are these two here. Everything else ends up being 0. And what it gives you is that the cross product of the location where this velocity acts multiplied by its velocity is just 1 times -1. 1 for this length, which is this, and -1 for this term here, which which is the velocity. And so the torque about that point is in magnitudes of 1 times minus 1 times a minus, which gives you plus. And so what that's saying is, in terms of our moment of momentum, if this is my z-axis, then it's turning, clearly trying to turn it, depends how you look at it, clockwise if you look down the z, I guess. And so in that direction, rotation is in the direction of my fingers. Rotation is in the direction of my fingers, and so that's what this positive rotational components define. Okay, so cross products do have some use, but we won't use it in that way. We'll use this simpler expression that we defined before, which is basically this. So we won't have to use anything more involved in this. Okay. So all right, let's go back. What else do we have to look at? Don't need to deal with that. We don't need to derive it because we already have. This is basically the derivation. Now, looking back on this, you remember for Reynolds transport theorem, we have an extensive quantity and an intensive quantity. If our extensive quantity is just mass times acceleration, this is rotational acceleration times mass. This is the same as, if you like, ma, right? This is Newton's law. Yeah, this is change in velocity. And so this term ends up, actually, so let me back off. This is mass times velocity. And then when you take the time derivative of this, it becomes acceleration. But this is just momentum. Happens to be rotational momentum. So we won't worry ourselves about that. It was much easier to be able to take this previous expression and just multiply both sides by r. And it's basically the same outcome. Okay? So let's use it for something. Yeah, let's do an example. So we made 2 points. And the 2 points were that we have this expression, which we can use, and we will use it. And so if we know for our simple geometry what the radius is, where it acts, we should be able to calculate what a velocity is relative to our chosen sign convention. Mass flow rates are the same as before. So mass flow rates is what? Positive if out, negative if in. Velocity is positive from our right-hand rule clockwise. Oh, counterclockwise. Counterclockwise, right? It depends how you're looking, I suppose. So we have to use, I can't draw a thumb very well. You have to use your right-hand thumb rule. These are your fingers. So this is up, and then this is positive round. And torques would be positive in the same direction. This sign convention isn't so important for this. And I guess we will want to use something else. And the other thing we'd like to use is that the velocities are equal to the relative velocities plus, I think in the notes here we'll use velocity of the control surface, CS. This is just the control surface. Static velocity relative to the control volume versus the motion of the control surface. Right? So those are the 2 expressions we'll use. I guess the other expressions we might want to use, which are useful, is that ultimately we can also use the idea that we can convert this into, we'll get a torque at the shaft, and we can actually convert this torque at the shaft into a rate of doing work. And so the same thing. If we know what the force is that's applied on the shaft, we know the rotational speed omega, and we divide by the amount of mass, then we can calculate the amount of shaft work per unit mass. But I think this is perhaps the easiest one. So the other term which is better is uppercase W rate is equal to T shaft multiplied by rotational speed. So this is the torque that gets applied. And this is how quickly it's going, and this will be in radians per second, right? And so this gives you the amount of power. So the rate of doing work is power. So this is what we've called before P. So the rate of doing work is power. It's multiplied by the shaft torque multiplied by W. So in other words, you can hold the sprinkler static. The torque will be large, but it will have no rotational speed, and so the work power will be 0. You can allow it to spin on its own, but you don't attach anything to hold on to it, like a generator, in which case the shaft torque will be 0, but the speed will be its maximum. And so it's the same as this previous example. It has to be some happy medium in between those, not static with a big force, not moving as fast as it can with 0 force, but the middle point of those. Okay? So those are the 3 expressions that we need. So maybe I'll write that here so at least we have them in the same place. So what was it? It was uppercase W dot is equal to the torque times rotational speed. So these are the 3 expressions that we might want to use. How do we use them? In a simple example. Okay, let's use the sprinkler example as our muse in this particular case. So we have an example with a sprinkler. It's the same as the one the dog was chasing around earlier on on YouTube. And so we won't worry about all these different components, but what do we have? We have 5 liters a second coming out of 3 nozzles. From these nozzles, presumably there would be a third of it coming out of each one. We have a cross-sectional area of the nozzle which is 18 millimeters squared. And the radius of the thing is 0.5 a meter. So that's the geometry. And so we can do 2 things. We can hold the rotor static and calculate the force that comes out of it as one end member. Or we can allow it to spin and we can calculate what the rotational speed is under that condition. And so that's basically the question. So how do we go about doing that? We use our expression that we had before, which was what? Torque is equal to velocity times mass flow rate. Did I leave out R in these ones? I think I might have done. No, I didn't. Yeah. So velocity times mass flow rate times R is equal to the torque. So that's what we're using. I guess we used uppercase M for mass flow rate. They use lowercase here. So mass flow rate, radius times the velocity. I guess I probably shouldn't have written it as theta. We want the tangential velocity. We always want the tangential velocity. That's at an angle here, which is a right angle. And in this particular case, if it's coming out at this velocity, then the component that's measured in the direction of the tangent to the circle is v cosine theta. And so this is v tangential. I think I call it theta. But so in other words, we can calculate that. We know the mass flow rate is 5 liters per second divided by 3 different tubes. So 5 liters per second and density allows us to put this in here. The output is going to be the volumetric flow rate. So this is 5 times 10 to the minus 3 meters cubed per second, because there's 1,000 liters in a cubic meter. And so the velocity out is going to be the flow rate out of each nozzle, which is Q over 3, and divided by the area of each nozzle. So that gives a velocity, right? Flow rate divided by an exit velocity. And so we have that. And what else do we need to do? So we have this velocity here. We know what this angle is. The angles are either 0, 30 degrees, or 60 degrees. The easiest one is if it's just coming out at 0. And as a result of that, we can substitute v theta into this. We know the mass flow rate, and we know that this is equal to half a meter. 0.5 meter, right here. And so we have all those terms. So we can calculate, just by resubstituting those, what the amount of torque is on the shaft. It just becomes an exercise in algebra. So if we do the calculation, let's skip straight to the results. If we do the calculation at 0 degrees, we get the force as 231 Newton meters. Force times length. If we do it at 30 degrees, we get the shaft torque of 200 Newton meters. And if we do it at 60 degrees, bless you, we get 116. So not so strange, right? If it's tangential, it takes the most force. As you make it wider and wider, it takes less force to hold in place. Ultimately, when it's at 90 degrees, you know it's going to take 0 force to do that. So the fact that these magnitudes are going down as you make it more oblique, more in line with the center of the circle, then isn't a surprise. So that's the one thing we can do. So that's one end member. The other end member is that we could apply no torque and allow it to spin. And so if we do that, then we can use the same expression, but now we need to incorporate the fact that we have this velocity that we should substitute into this expression here. So let's go down and look at that. We're going to allow it to turn. So now our expression is again t is equal to the velocity, which is tangential, times the mass flow rate times r. R hasn't changed, mass flow rate won't change, but the velocity has, right? The velocity is equal to the relative velocity across the control surface plus the velocity of the control surface, which here they call u. And so in this particular case, we've assumed that u is 0, and therefore we can make that substitution. That's just fine. In this case, our u is not going to be 0. And so when we write out this equation for the shaft, mass flow rate, which is this, the radius at which it acts at, which is this is going to be half a meter. This is going to be 5 liters per second divided by 3 nozzles, whatever that is. So that hasn't changed. But now the velocity term has to include these. W out, as if I move this down, is going to be equal to the rate of flow out of here multiplied not by the direction here, but in the direction tangential to this. And so this now is the rate of flow out of the nozzle and the inclination of it relative to the tangential. And this term now is the velocity of the control surface, what we've called VCS. And so we have to remember our sign convention. We're looking down on this nozzle. We're using our right-hand rule. So I'm looking down the axis on top of this. And so this clearly is the positive direction. And this flow rate out of this component is in the positive direction, which is this W here. But the velocity of the control surface that will turn is going in the opposite direction. So this, if we wanted to do it impartially, we could put this as this term plus this, in which case we'd end up with a magnitude which was negative, which would mean that it's just going in the opposite direction through W. But the reason in this particular case is that this negative term is because the direction of rotation that we've chosen to take as positive in this case is in the negative direction. And so this has to be negative. Okay? And so if we do that, we can substitute for the fact that the velocity at the edge of this circle, if the velocity is equal to u out, then that's the same as doing a radial tangential velocity, a radial rotation rate, omega radians a second, multiplied through by whatever the lever arm is. So this is the lever arm. And so if you solve those by substituting this into this expression here, we know that the torque on the shaft is 0 because we're letting it spin. We know the flow rates, mass flow rates, and the radius. We also know the flow rate out of the nozzle because it's related to the mass flow rate in some way. And the only unknown we have is the rotational speed. And if we do that, we can solve for the rotational speed, which is this expression here. And it's just algebra after you make these substitutions. So in other words, you substitute this into here, you set this to 0, and you solve the equation for that. And as a result, what do we expect? So we said that when we hold it in place and the angle is 0, we have the maximum force. Not surprisingly, if we release it for that maximum force, when the water is flowing out tangential to the circle, like this, it's the highest rotational speed. When it's flying out at 30 degrees, so like this is 30 degrees, then it's a lower rotational speed. And when it's coming out at, is it 45 degrees? No, 60 degrees. And in the final case, when it comes out at 60 degrees, then we have the lowest. So not surprising. So what's the moral of the story? I guess we've shown, whoops, long way. The moral of the story, I guess, is we've shown what you kind of knew by intuitively. If you have the jet angled tangential to it, you'll get either the maximum force or the maximum speed if you release it. If you have it progressively more inclined to that, then it'll be slower and slower. When it's directed straight through the center of the sprinkler, obviously it won't turn, and there'd be no net force either, because there's no lever arm applied to that. And so our extension, if you like, to being able to look at moment of momentum is really just an extension directly from what we've talked about in terms of linear momentum. And the equation that we'll use is kind of the same. And really the only expressions you need to know are the moment of momentum equation with one term. You need to be aware of the fact that it matters whether you hold it static or allow it to turn, because there's a relative velocity involved. And that is really, and that these things are actually the essence of how you turn work, how you turn force and velocity into power. Power is the product of force times velocity. And so if either one of them is 0, you get no power out of the system. If both of them are non-zero, you get some power out of the system. And you can optimize the system to get the maximum. And in our simple cases that we've talked about, that maximum may be somewhere in between them. Not exactly in between them, we haven't really showed that, but we've kind of assumed that.